Okay, so I now want to discuss a little bit about how Greeks counted and how they named numbers. And notice that I have the computer back on my desk. I'm going to try to get a stand so it's a little bit closer, but I was nervous about having it on the back of my chair. So you know about Roman numerals, I would assume. I'm not going to talk to you about Roman numerals, but I do want to talk about how Greeks represented numbers, and maybe from that a little bit, we can tell a little bit about how they thought about quantity, I think, from this. So they had a ciphered system similar to the hieratic system that we learned about with the Egyptians, and I have our letters for the alphabet here, but they had their letters for the alphabet. But it's just better, I think, easier if I just use our alphabet to explain what's going on. The letters A through I represented the numbers 1 through 9. The letters J through R represented the numbers 10 through 90. And then these letters here go from 100 to 900. I needed an extra letter, so I just used a square down here to represent 900. And so if they wanted to represent a number, let's say they wanted to represent 764, then they would write this in the following way. They would have a 700, which is y, 60 would be x, and then 4 would be d, like this. Now, if you think about trying to do math with numbers like this, I think you will see that there's a challenge here. I mean, a lot of the ways that we think about math is not really possible using a system such as this. For example, the fact that 60 is just 10 times 6. For this system, we can see that just by adding a 0, but there's not an obvious connection between F and O here. Or, going from 80 to 800, we just see that we add a 0, or going from 8 to 800, we add 2 zeros, but just the letters themselves, there's not an obvious connection between H and Z unless you just have these things memorized. So stuff like that, even these kind of basic tricks that we have when doing mathematics is kind of not available in a system like this. And then maybe you can even think about how challenging doing things like carrying and stuff like that would be if you want to do long multiplication and stuff like that. Anyways, as it stands, with the numbers listed here, the biggest number that they could write would be 900, which is represented by a square, 999, so R, I. Using this system as I've laid it out here, they could write the biggest number would be 999, but they had a pretty cool trick, which is all of the letters from A to I, they could write a prime in front of it to get 1,000. So, for example, if I did prime I, this would be 9,999. So using this system here, they can get all the way up to 9,999. Now, I'm not sure why they didn't, also do that with, put a prime on these other ones as well. I don't know about that, but that would be an interesting question, and will be one of the discussion questions as well. Anyways, so we have this. Now, one more than this is going to be what they called a myriad. And I'm going to represent it with a fancy M. So this is 10,000. Now, if you wanted to discuss the number of myriads, so like 2 myriads would be 20,000, you would put it up here in the exponent. So something like this with a B would represent 20,000. Okay, now let's think about how things like this are going to work, or the size of the numbers that we can talk about. So without the myriads, using the biggest system that we can over here, we can talk about, the biggest number that we can talk about is 9,999. So we could do something like this, so prime I, this R I. This would be 9,999 myriads. So in other words, 9,999 times 10,000. So 9,999 times 10,000, which is just adding 4 zeros. So 1, 2, 3, 4. And so from this, we can get up to 99,990,000 using myriads. But notice that we still only have 4 digits of precision here, which kind of makes sense. I mean, when we're dealing with numbers of this magnitude, very often this is all of the precision that we need. Now, obviously, if you're doing very precise scientific work, you need much more precision than that. But okay, this is a reasonable amount of precision, I think, in everyday life. Okay, however, this what if we need bigger numbers? Okay, so let me pose the question that was posed, or that Archimedes answered. How many grains of sand? Whoops. I can't. How many grains of sand are there? How many grains of sand are there? And this is kind of like a challenge to name the biggest number that we can name, okay? Because there's probably more than, I think, the number that I had written there was 99 million. There's probably more than 100 million grains of sand. We probably recognize that. And so maybe they probably also recognize that there's more grains of sand than they have numbers to discuss. So is it an infinite number of grains of sand? Of course, we know the answer to that is no. Okay, so Archimedes wants to discuss and come up with a system for writing arbitrarily large numbers. Okay, so the first thing he did was he came up with this idea of a myriad of myriads. Okay, it makes sense using the available terminology that they had. Myriad of myriads, I will write it like this. And so now what is this? Well, a myriad is 10,000, and we're doing a myriad of myriads, so it's going to be 10,000 times 10,000, or 10,000 squared. And then this is going to be 1, 2, 3, 4, 5, 6, 7, 8. Okay, ran out of room here. Like this. Yes. So 100,000. So in other words, using the available language that existed at the time, you could talk about a myriad of a myriads, and that gets you to 100,000. Okay. Now, Archimedes called the set of first order numbers were the numbers up to a myriad of myriads. In other words, all the way up to 100,000, which it's convenient to think about this as 10 to the power of 8. So all of the numbers up to 10 to the power of 8. Okay, well, the second order numbers, so we have this sort of inductive process going on. The second order numbers are going to be a myriad of myriads of first order numbers. Okay, so we start with myriad. From that, we can have a myriad of myriads to get first order numbers. And so second order numbers are going to be a myriad of myriads of first order numbers. Okay, so this is going to be 10 to the power 8. That's a myriad, and we want a myriad. That's a myriad of myriads, and we want a myriad of myriads of first order numbers, and so this is equivalent to 10 to the power of 8 squared. Okay, it's essentially a myriad of myriads of a myriad of myriads, and so this is 10 to the power of 16. Well, okay, we can go this. Third order numbers would be all of the numbers up to 10 to the 8 to the power of 3, and so on and so forth. Well, we can do this all the way up to, what is the biggest number that we can put there? Basically, it's going to be a myriad of myriads. In other words, 10 to the power of 8. So we can go all the way up to 10 to the power of 8. and this is going to be equal, this is going to be equal to 10 to the power of 8 to the power of 10 to the power of 8. Okay? Now, okay, sorry about that. So it's 10 to the power, anyways, 10 to the power of 8 to 10 to the power of 8. Now, what is this? Well, 10 to the power of 8 is 100 million, and we multiply it by 8 is 800 million. So this then is a 1 followed by 800 million zeros. And so the question is, well, is that enough? Is that enough grains of sand? Or how many grains of sand are there? And as we will see, Archimedes used a much smaller number than this, but it's still a very big. The number of grains of sand is still very big. Okay, but setting the so-called practical question of how many grains of sand there are, well, why stop here? Okay, so what Archimedes next said was, okay, the first period of numbers is going to be all of the numbers up to this point, and so on and so forth. You can do the induction process like this indefinitely. You just have to come up with different, words instead of, orders and periods and that sort of things. It's just, okay. Definitely the way that they wrote numbers caused them to think about things a little bit differently than we did and kind of hamstrung how they could express themselves. But this is what they used. Okay, another thing that I want to mention is Archimedes, his estimate was that there are 10 to the power of 51 grains of sand using the size of if you had 10 to the power of 51 grains of sand, you could fill his known universe with that many grains of sand, and using a slightly larger size of the universe, you would need 10 to the power of 63 grains of sand to fill the universe, which those are well within the set of numbers that he could come up with here. Okay, all right, and so for practical purposes, this is probably the biggest number that we would need to use to do scientific things. Now, obviously, we need more precision to do science and stuff like that, but that's not really available here. There's still going to be a very limited precision that you can have in numbers like this. All right.